Okay, so if we are doing the chain rule backward and achieving that with an integral or an antiderivative, we use a process that we call U-substitution. So let's take a look at an example of this. We're going to start with an indefinite integral example. So the indefinite integral of x cubed times cosine x to the fourth plus 2 dx. So all this is looking for is the antiderivative of this. Like, what would I take the derivative of to get this? And that's not like immediately clear. And the way we do this is that we do a change of variable. So I'm going to grab this here, and we're going to call that u, and make that x to the fourth plus 2. Now the trick to this is we're going to take the derivative of that with respect to x. So we get du dx is equal to 4x cubed, which if I rearrange that, I get that dx is equal to du over 4x cubed. And you can kind of convince yourself of this by using some multiplication rules or cross multiplication. It's not too over the edge there. So now we're going back into our indefinite integral. The x cubed is still here. This is now the cosine of u, because that's what u was, is that value. And then dx is now this, so this is du over 4x cubed. And in a U-substitution situation, you're going to get a cancellation. So this x cubed and that x cubed are going to cancel, leaving me with the indefinite integral of the cosine of u, and then I can bring 1/4 out front to account for that 4 du. And the indefinite integral of the cosine is the sine of u plus some constant. And back at the beginning, u was x to the fourth plus 2. This is 1/4 sine of x to the fourth plus 2 plus some constant. So this is a pretty straightforward example of a U-substitution problem, all right, with an indefinite integral. What might be a good idea here is actually to go and take the derivative of this and see if you don't get the integrand back. And it's a neat little experiment to see what would happen and prove to yourself that this is in fact the antiderivative. Okay, so let's look at a second example of this. Okay, so our second example here is going to be the indefinite integral of the square root of 2x plus 1 dx. Now this seems like pretty innocuous, but if you kind of get into it, there is a chain rule embedded in here. So we're going to play this game again. We're going to let u be equal to 2x plus 1, which means that du dx is equal to 2, which means that dx is equal to du over 2. So when we rewrite this integral, we're going to get u to the 1/2 times du over 2, right? So let's see what happens here. Well, the 1/2 is coming along for the ride, this 1 over 2. I'm going to get u to the, let's see, 1/2 plus 1 is 3/2, which means I need a 2/3 up here, plus c. Let's see, the 2's cancel. So this is going to give me 1/3 u to the 3/2 plus c. And again, if you want to, you should then, we got to resubstitute, right? We got to put that u back in. This is going to be 1/3 of times 2x plus 1 to the 3/2 plus some constant. Okay, So if you want to, you can go back and again try to take the derivative of this and show that it gives you the square root of 2x plus 1. That should be fairly straightforward. We're going to use this same integral, but we're going to use it as a definite integral, and we're going to show you two methods for dealing with this as a definite integral. Okay, so the first method is what I'm going to call a change and change back method. It's probably the more intuitive of the two methods, but it's also the longer one. So we're going to take the definite integral from 0 to 4 of the square root of 2x plus 1 du. Okay, so again, we let u equal 2x plus 1. That turns into du dx is equal to 2, which means that dx is du over 2. Right? So what I'm going to do here is I'm going to do exactly what I did last time, except for I'm going to be very specific that this is x is 0 and x is 4. Okay? And then this is going to give me u to the 1/2 and du over 2. Okay, so again, I can bring that 1/2 out in front. The antiderivative is going to be u to the 3/2, which means I need a 2/3 in front of that. And this is from x is 0 to x is 4. Right? So the 2's cancel. This gives me 1/3 u to the 3/2. X is 0, x is 4. Okay, so I did the change here, and now I'm going to do the change back. So this is going to be 1/3 times 2x plus 1 to the 3/2 from 0 to 4, because now I'm only down to just there being an x variable. Okay, so we substitute in the 4, so that's going to give me 8/9 to the 3/2. Minus, when I put the 0 in, that's going to be 1/3, 2 plus 1, or 0 plus 1 is 1 to the 3/2, right? Okay. So let's see, that's 1/3, 9 to the 3/2. So the square root of 9 seems to be 3 to the 3rd is 27. 27. And then 1, square root of 1 is 1 to the 3rd is 1, right? So this is going to be 27 over 3 minus 1 over 3, which makes this just 26 over 3. Okay, so the indefinite integral resolved to a real number. All right, so this is the change and change back method. So here, I changed from x to u as my variable, and then came back to here and changed it back to x, put in my bounds of integration, and got, using fundamental theorem of calculus, a value for the indefinite integral. So let's look at the second method. Okay, in the second method, we are going to change the bounds of integration. Okay, so exact same problem. We're going to get the exact same answer. Methodologically, we're going to change the game a little bit, right? So we're going to go the integral from 0 to 4 of the square root of 2x plus 1 dx. We're still going to let u equal 2x plus 1. We're going to let du dx is equal to 2, which still implies that dx is du over 2. Okay, so this now is going to give me still u to the 3/2. Still gives me a du over 2. But now we're going to change the bounds of integration from being x values of 0 and 4, right? But if I put them into here, these are now going to be u values, right? So 0 plus 1 is 1. 4 times 2 is 8, plus 1 is 9. So now I've just kind of put everything in terms of u. I don't need the x's anymore, right? So again, I have a 1/2 here, right? And then I'm going to get, oh, sorry, that should be u to the 3/2. That should just be u to the 1/2, right? So I'm going to get u to the 3/2. Got to step aside myself there, times 2/3. But now I'm already just going to evaluate it at 1 and 9. So the 2's cancel out. This is going to give me 1/3 times 9 to the 3/2 minus 1/3 times 1 to the 3/2. Okay, so you're seeing I'm cutting a whole bunch of steps here by just changing the balance of integration at this point. So the square root of 9 is 3 to the 3rd is 27 over 3. And I'm going to subtract 1 over 3 from that. And I'm going to get the very same 26 over 3. So it doesn't matter which way you do this. And in fact, like when I was the high school student sitting in your seat, I would have always done this by the first method because I wasn't as cautious with my placement of numbers. But I'm very comfortable changing the balance of integration midway here now, and I find that this is much quicker. If you can pull that off, it's a good idea because the AP exam is, of course, a timed game. And if you can pull the balance of integration in and feel confident in doing that without having to change it and then change it back, that's always probably a good move. All right, so undoing the chain rule through U-substitution.